Hello, everybody. Here's the third of the lectures for the digestive system. There's 4 lectures, and after that we'll have the test. Today we're going to put together a lot of the things that we talked about in the first couple of lectures. We talked about how the system is laid out. We talked about the propulsion mechanisms through the system, and then the secretions at each step along the way. Today we're going to move the food into areas, we're going to secrete the right stuff, and then we're going to talk about what happens, the digestive process, and then how we absorb it at the intestinal wall. First of all, our main digestion and absorption is the macronutrients, carbohydrates, fats, and proteins. Note that carbohydrates are shown as CHO, carbohydrate, often. So when you see that abbreviation for carbohydrate, remember what it is. These are large molecules. They all need to be broken down before we can absorb them across the intestinal wall. The primary mechanism we use is what's called hydrolysis. And with hydrolysis, you break a large molecule down by adding hydrogen to one side and OH to the other side. That's H2O. So when you add water, you break the molecule in half, or you break off a piece of it. To condense it, you would remove that H2 and O and stick the pieces back together. But right now we're planning to hydrolyze or break apart or digest our macromolecules so that we can absorb it at the brush border. Remember, we call the wall of the small intestine the brush border because those microvilli look like velvet. Carbohydrates, polysaccharides, starches, and disaccharides, which are 2s. They're formed by bonding monosaccharides, which are just one ring, which is either glucose, galactose, or fructose. You put a couple of those together, you have a disaccharide. You put a bunch of them together, you have a polysaccharide. Fat is triglycerides, mostly. We have some other fats. These are 3 fatty acids that are bonded to a molecule of glycerol. It forms a backbone. I'll show you in a second. And you have to take a couple of those off before it's a small enough molecule to be absorbed. Peptides are small groups of amino acids. Proteins are bigger ones. Polypeptides, you have more and more peptides. A dipeptide is 2 amino acids. Proteins are large, complicated structures, and you'll need a variety of proteases to bring those down. Typically, what you'll do is take off an amine group that forms it's a nitrogen group, and then you break the rest of the amino acid into small dipeptides or small polypeptides. So here's your main starches. Amylose is the one where we get our starch breaker down, or enzyme's name, which is amylase. Amylase breaks down amylose. Amylose is just a whole bunch of glucoses, glucose, all stuck together. If you were to break this apart, you could get a disaccharide, you could get a small polysaccharide, you could get a monosaccharide if you broke it far enough. Generally, we don't break it down that far immediately. And amylopectin requires a slightly different enzyme, but often we just refer to amylase as, at least at this level of teaching, as the enzyme that breaks down starches. Amylopectins is that same amylose structure with some side chains, also glucose. It's all glucose. There's nothing in here but glucose. So here we have a starch. And if you want to break it down, you can break it down into 2s. 2 glucoses are called maltose. And if you break it down into something slightly larger, it's called a dextrin, a limit dextrin, or an alpha limit dextrin. You see it here, alpha limit dextrin. It's just a slightly larger molecule of glucoses that needs to be broken down by a different enzyme than you would need to break these guys in half. Your disaccharides, of which this is one, sucrose, table sugar, maltose, which is this one, which you get a lot of when you break down starch, and lactose, which you get from milk. That's lactase breaks down lactose, maltase breaks down maltose, sucrase breaks down sucrose. It's all named pretty well. Here is a typical triglyceride. It's a glycerol molecule here with 3 fatty acids struck onto it. When one breaks loose, it's called a free fatty acid. So this is a free fatty acid, this is a free fatty acid, and this is a monoglyceride instead of being a triglyceride. Monoglycerides and free fatty acids are all small enough to be absorbed. So your digestive process is designed to turn these into these. Proteins are a lot more complicated. They're so bent and twisted and held together by hydrogen bonds into these tertiary coils and stuff. So what we use, we start off with stomach acid, hydrochloric acid. It breaks those initial tertiary bonds and unravels it into a longer, thinner spool. And then a variety of proteases, peptidases and proteases, are designed to break this down. And they have several different names. I'm going to need you to know maybe 4 of them, the most important ones. So naming them, they're pretty good. You know, fat is lipid. So breaking down lipid, you use lipase. Amylose is starch, so you use amylase. So your primary breaker downer of big carbohydrate molecules is amylase. Sucrose is broken down by sucrase. Maltose is broken down by maltase. Lactose is broken down by lactase. Those limit dextrins, you have another enzyme that breaks those down. It's called alpha dextrinase. And you have lots of peptidases and proteases that break down different types of protein structures. Again, I'm only going to ask you to know a few specific ones. If you remember, carbohydrate digestion starts in the mouth. Salivary amylase. Salivary amylase is your digestive enzyme that is made in saliva, and it starts the breakdown of starches while you're chewing it in your mouth. There is a salivary or lingual lipase, salivary lipase. It has a relatively small effect, mostly on things like palm oils and things like that. So you could do without it. It is there. If you see it mentioned in the book and stuff, it is there. Oops. My computer loves to do that. I'll keep going back. Remember, pepsinogen has to become pepsin inside the stomach. Pepsin is your first protease. It starts the breakdown of proteins. Pepsinogen is activated by hydrochloric acid to become pepsin after it's already entered the stomach. And that pepsin starts breaking down your proteins. Also in the stomach, remember, we produce hydrochloric acid and intrinsic factor. You also produce gastrin in the stomach lining, which causes you to make hydrochloric acid. And then, as I said before, the pancreas is the big guy, the big player. It makes pancreatic amylase, which is super strong and will break down the rest of your starch, whatever your spit doesn't do. Pancreatic lipase. This is where your fats get absorbed, digested. It's in the intestine. It doesn't really start in the mouth or the stomach. Your fat digestion really begins in the duodenum when the pancreatic juice gets dumped in through the sphincter of Oddi. You have some other lipases for breaking down cholesterol and phospholipids, which are cell membrane lipids. Remember that these are there. There are always some other things that are there, but these are the guys I want you to know there. And then you have proteases. And here we have 3 of them. They're real important. We already have pepsin. Remember, that comes from the stomach. We have pepsin that comes from the stomach. And then from the pancreas and into the intestine, dumped in at the sphincter of Oddi, you have trypsinogen. Where's my cursor? Trypsinogen, chymotrypsinogen, and procarboxypeptidase. Now, ogen is like pepsinogen, gets converted into pepsin in the stomach. All of these have to be secreted in a form that won't digest your pancreas. So these are precursors. Trypsinogen becomes trypsin. Trypsin is the actual digestive enzyme, but your pancreas makes trypsinogen, so you won't digest your own pancreas until it gets into the intestine. Chymotrypsinogen. This becomes chymotrypsin. Procarboxypeptidase. Pro means before. Why didn't they call it carboxypeptidase-inogen? I guess it's hard to say. So procarboxypeptidase is the third one. It becomes carboxypeptidase. Trypsin, chymotrypsin, carboxypeptidase are your 3 primary protein digesters that come out of the pancreas and into the intestine at the sphincter of Oddi. Now, not only do we have these pro-enzymes coming out that haven't been activated yet, interestingly, when you get into the intestine, as soon as this one activates, this guy activates these guys. So while it's in the pancreas, we produce a trypsin inhibitor to make sure this guy doesn't get turned on too soon. Because if he does, he'll go ahead and turn these guys on and you'll digest your own pancreas. It happens to people with pancreatic disease or a blockage of the pancreatic duct. The stuff can't get out fast enough and it starts activating and starts digesting your own pancreas. And then at the brush border itself, the cells of the intestinal wall make some final enzymes: sucrase, lactase, maltase, alpha-dextrinase, to digest your carbohydrates and the final digestion. Okay, so now we're going to do carbohydrates first and see how they get digested. First of all, most of the carbohydrate we absorbed is starch, which is glucose. And, it's either amylose or amylopectin. But these are all big strings of glucose molecules that can be broken apart. You also eat a lot of cellulose, which is a starch. This, for us, is non-digestible because we don't make cellulase. Cows and horses make cellulase, so they can digest grass and turn it into sugar. They can break it down. We can't. This becomes our non-digestible bulk fiber. So we like eating cellulose because it helps our intestines work better. It helps keep them moving better. Then we eat some sucrose, which is table sugar, which is a molecule of glucose and one of fructose. These are disaccharides. It's a glucose-fructose. Lactose, which is milk sugar, which is glucose and galactose. These are your 3 monosaccharides: glucose, fructose, and galactose. You just combine these 2 to make table sugar. You combine these 2 to make lactose. And you combine 2 glucoses to make maltose, which is what you get when you break starch down. We also get a little bit of stored carbohydrate when we eat meat. We get it from glycogen that was stored in that animal's muscle. So the digestion of carbohydrate begins in the mouth. Carbohydrate begins in the mouth with salivary amylase. It breaks primarily amylose down into maltose, into tubes. It breaks a lot of your long starch molecules into glucose, a disaccharide. Some of it will wind up in those small polysaccharides, those alpha dextrins. Both these and these will need to be broken down the rest of the way later. Because we don't chew very thoroughly. I know when I'm eating, I put it and chew it a few times and ram it down my throat so I can cram more food in my mouth. So we don't really do a ton of digesting in the mouth unless we're somebody that chews really thoroughly. But the salivary amylase will continue to work in the fundus, the upper part of the stomach, for a while before it gets inactivated by the stomach acid. So you chew it, you mix it with some salivary amylase, and you swallow it, and the salivary amylase continues to work for a while and absorbs or digests, breaks down a decent part of the starches before it moves on farther. There are no amylases in the stomach, produced in the stomach. So once it gets squirted into the duodenum, in through the sphincter of Oddi comes the pancreatic juice containing pancreatic amylase. And it's so powerful that it'll digest all of your starch, even if your spit wasn't doing the job very well. So it's a very powerful starch breaker downer. You basically digest all your starch. You digest and absorb all of these nutrients. You don't poop them out. So whatever you eat, enjoy it, because it's going to add to your caloric intake whether you want it to or not. Initial hydrolysis of starches, salivary amylase, then pancreatic amylase. And so by then, you have a bunch of maltose and limit dextrins in your intestine ready for their final processing. Now this is one of those things that looks terrible when you first look at it, but this is really easy. This is the brush border of your intestine. Here's the inside of your intestine. This is your tissue. Here's the food. The food is out here. It's coming across, and it needs to get across the brush border and into your bloodstream. So the lactose has to be broken down into glucose and galactose. You can only absorb monosaccharides. You can absorb glucose, galactose, and fructose. You can't absorb anything bigger than that. So you have lactase, which breaks down lactose into glucose and galactose. Glucose and galactose can both go through this cotransporter powered by sodium and pushes it into your bloodstream. Now, if you get sucrose, sucrose comes in. Sucrose is glucose and fructose. The glucose, it gets broken in half by sucrase. Sucrose gets broken in half by sucrase. The glucose goes through this same transporter over here that takes glucose and galactose, while the fructose has its own transporter. Fructose is a facilitated diffuser. It's a little slower. Fructose doesn't absorb as fast. That's okay. You don't have as much of it. It's fine. But all you have are these two transporters. That's it. All your glucose and galactose goes through here, and your fructose goes through here. Your alpha limit dextrins, what are they? Those are blobs of glucose molecules. So you have alpha dextrinase. It breaks it into glucose, which goes through here. So you take everything you have, you take your lactose, your sucrose, and your starches that have become maltose and limit dextrins, you break those into glucose and galactose to go through here, and fructose to go through here. And all of your carbohydrates have now entered your bloodstream. Lactose intolerance. It's easy to see how that could happen. Lactose intolerance is a big deal around the world. Half the world's population has at least some degree of lactose intolerance. People who stop drinking milk after they're weaned from their mother's breast are most susceptible, because if you don't use it, it atrophies and you become incapable of making lactase. If you can't make lactase, the lactose that you get from milk and dairy products stays lactose in your intestine, and two things happen. The bacteria in there in your intestine love to feed on it, so they multiply and give you a really upset stomach. They also produce a lot of hydrogen gas, which makes you very flatulent, which is really unfortunate. And then also the all of this glucose and galactose is supposed to move into your bloodstream, and it draws water with it by osmosis. If it stays in the lumen of your intestine, it draws water into the intestine and gives you diarrhea. So all of this lactose staying in your intestine gives you the symptoms of lactose intolerance, which is diarrhea and gas and cramping pains and that sort of thing. Undigested lactose, nutrients. And anybody can develop it, especially if you're not a big milk drinker. Some people just lose the ability to make lactose anyway. You can also have a sucrase deficiency. Similar deficiency in the ability to make sucrase means that you can't digest sucrose, so you can't absorb it either. Now this is worse. Lactose intolerance, you can just avoid all dairy products and you're fine. You can also take some lactase supplements, and help you, enjoy a ice cream cone or something sometimes. But sucrose, table sugar is found in everything, especially all of our processed foods. And so it's hard to avoid eating sucrose. Just a second. Sorry, my phone was ringing. But the result is similar. If the sucrase stays in your intestine, you have gas, you have osmotic diarrhea, and you feel very similar to lactose intolerance. Okay, so that's carbohydrate. So, what I want you to be able to do with all of these guys is to be able to say, starts in the mouth with salivary amylase that breaks down the starches into twos and little ones, to maltose and limit dextrins. It goes into the stomach, where the salivary amylase works for a while longer. It goes to the intestine, where pancreatic amylase gets in there, breaks it down really well into maltose and limit dextrins. Then at the brush border, you break down your sucrose and your lactose and your maltose and your limit dextrins the rest of the way, and then you absorb them. Okay, if you can say that, that's a pretty good, that's going to answer most of the questions I'm going to have for you about carbohydrate absorption. So let's talk about fat digestion. Fat digestion is a little bit more complicated. Triglycerides mainly, we talked about that. That's 3 fatty acids bound to glycerol. We got to break them down into free fatty acids and monoglycerides. We get a little bit of milk fat and phospholipids and stuff and cholesterol from other things that we eat. But mainly, we're talking about breaking down triglycerides, because that's most of our fat intakes. A little bit of lingual lipase. Milk fats, coconut and palm oils. It can help if you have deficiencies in your other lipases. But for the most part, you can forget about that. From our point of view, fat digestion really takes place in the intestine with pancreatic lipase. In the duodenum with pancreatic lipase. It's strong. It's going to do the job. And that's where bile is, where it can help you to digest your fats. So the first thing we have to do is we have to emulsify the fat. The fat enters your stomach and into your intestine in big blobs. like if you dumped fat in your kitchen sink, it would be in big blobs floating on the top. It doesn't dissolve in water. But if you put a bunch of dish soap in there and stir it around really well, it breaks up into more like gravy, into tiny little microscopic droplets that look like they've disappeared. They're not digested yet, but it's undigested, but it is broken into such small, tiny pieces that can now float around in your intestine that your pancreatic lipase can get to it to digest it. And the product that causes this emulsification is bile. Bile has a fat-loving side and a water-loving side. The fat-loving side sticks onto the little fat droplet, and the water-loving side allows it to stay in suspension so it can float around in there and get digested. Remember, bile is produced in the liver. Cholesterol is the primary component of bile. It gets stored in the gallbladder, and then it gets squirted into the common bile duct, and at the sphincter of Oddi, it enters in when it is stimulated by CCK. CCK stimulates both bile release and pancreatic juice release. Secretins causes more bicarbonate to come in. So CCK will cause your digestive stuff to come into the duodenum where the food is. So here we have it again. We have the small hepatic ducts or bile ducts, bile ducts coming from all places throughout the liver. They join into this common bile duct here. The cystic duct goes off the side here into the cyst, which is the gallbladder. A cyst is any fluid-filled bag. The bile is produced, it goes in here, and it concentrates. You pump water out of it to make it more concentrated so you have a greater powerful stuff. And when fat enters the duodenum, it binds to receptors that signal the pancreas to squirt pancreatic lipase into here, and the gallbladder to squeeze to squirt bile in here. The bile emulsifies the fat so that the pancreatic lipase can digest the fat. Here's bile. It has a water-loving side. It has a fat-loving side. Hold on. Emulsification happens when this big fat blob that you ate becomes tiny droplets of triglycerides and a couple of other kinds of fats, and it's got bile around it that keep these tiny droplets suspended in the chyme of your intestine, so that the pancreatic enzymes can now get to these guys and digest them. You got to take this triglyceride and get those monoglycerides off of there, those free fatty acids off of there, leaving monoglyceride behind. And you can't do that when you have a big blob and you can't get to the middle of it. So this emulsification process brings these into tiny droplets, not digested yet droplets, but now the lipases can get to them. So the major player is pancreatic lipase, response to acetylcholine, which is the parasympathetic nervous system, but also CCK, which is released when there's fat around. A lot of pancreatic lipase in your pancreatic juice. It squirts into the sphincter of Oddi. At the same time, you release bile from the liver. It breaks the fatty acids into free fatty acids and monoglycerides so they can be absorbed. Here we go again. You're breaking two of these bonds with your pancreatic lipase, so you have a monoglyceride and two free fatty acids. And then this digested fat is still fat. It won't dissolve well in your bloodstream. I mean, you already got your fat droplets tiny so you could digest them. You break all this stuff apart, and then it immediately comes back together, surrounded again by bile, to get it back out of solution so it can stay floating around in your intestine. And these digested blobs are called micelles. Now, this is where it becomes a pain in the butt for people trying to learn the fat digestion thing. You get a big blob, you emulsify it into little blobs with bile, you digest it, and then you put it into a third blob called micelles. These are digested fats ready to be absorbed. Now these micelles, see, here's a micelle. It's got, it's got your fats in it. It's got monosaccharides and monoglycerides and free fatty acids and little bits of some other stuff. But remember, we're talking about the triglycerides. So right here, we're looking at the monoglycerides and free fatty acids. These just run into the brush border, and they can move right across because fats can cross the membrane. So you don't need a transporter to get fat across. You got to get it into monoglycerides and free fatty acids so it can go, but it goes across when you hit. So the monoglycerides and free fatty acids move across the brush border into the cell, the enterocyte, or digestive tract cell, small intestine cell. So here we have the undigested blob. It digests and reforms into a micelle and then moves across the border. Now it's inside your cell. Protein digestion pretty much is like carbohydrate digestion. We mostly take in, most people take in more animal protein than plant. You can get protein from animals and plants. Average intakes is about 125 grams a day. We need about 40 to 50 grams per day. You also get some more protein from the GI tract itself, which is constantly sloughing off cells at the tips of the villi where the oxygen levels are kind of crappy. And so you're digesting your own cells and reusing them, recycling. Protein digestion, as we know, begins in the stomach. Stomach acid denatures it, which causes it to unravel itself, so that the pepsinogen, which becomes pepsin, can start digesting the protein into smaller pieces. So here's remember the sequence here. You eat protein, it binds to your receptors on your gastrin cells, your G cells. Gastrin then activates these ECL cells to make histamine. Histamine activates the parietal cells to make hydrochloric acid. Hydrochloric acid then activates this pepsinogen into pepsin. And then finally, the pepsin can start breaking down the acid. So it's kind of a lot of stuff to remember. But look, protein, gastrin, histamine, HCl, hydrochloric acid, pepsinogen, then you got pepsin, and then you can start your digestive process. All this happens way down in the pits. You release hydrochloric acid and you release pepsinogen. Pepsinogen is activated by hydrochloric acid into pepsin. Pepsin then starts breaking down the proteins. So that's the way to look at it. And you don't want it activated till it's out here, because you don't want it to start digesting your own tissue. And as with everything, the pancreatic secretions are the most important and the most powerful. Again, because you had stomach cancer, you had most of your stomach removed, you can live. You might not be able to make intrinsic factor, and you might have to take B12 shots for the rest of your life. But, if you don't have pepsin, your pancreatic enzymes will be able to digest your proteins okay, as long as you don't have massive amounts coming in at one time. Majority of the protein digestion takes place in the duodenum and the proximal jejunum using your pancreatic proteases, which we mentioned before. Pancreatic proteases come in with the pancreatic juice. When protein enters the stomach and the duodenum, it causes you to make gastrin, to make HCl, to activate pepsin, to start digesting the protein. It also causes you to release CCK. CCK causes bile to come in to help out with fat. It causes pancreatic juice to come in to help digest fat. And it's also full of these protein digesters. So CCK is telling the pancreas, here's food, send in plenty of proteases, let's digest the proteins. Remember, they come in as proenzymes and then have to be activated after they enter the stomach. So here they come. There's bile coming in here. It's going to help out with fat. Here comes the pancreatic juice full of these proteins. We have trypsinogen, chymotrypsinogen, and procarboxypeptidase. Trypsinogen is activated by an enzyme in the intestinal wall into trypsin. And then it activates the other guys. So we have a trypsin inhibitor here to keep it from activating too soon. And then we have an activator here. It's called enterokinase, intestinal turnaround. It takes their trypsinogen, turns it into trypsin. Trypsin activates chymotrypsin and carboxypeptidase. And then you have some brush border peptidases to do the final digestion. Again, it's a lot like your carbohydrate, where you start in the mouth and then you have your main digesters from the pancreas, but then you get to the brush border and you need sucrase and maltase and lactase. Okay, well, here are the proteins. They started in the stomach. Pancreatic peptidases break them down pretty far. So what you have are some small peptides, di and tripeptides, and you have, what you're going to need to do is break this down more. Now, you don't have to break it down quite as much as you broke down your carbs. Carbs have to be monosaccharides to get through. Proteins can be broken down into individual amino acids, which have, each of them has its own transporter. This isn't just one amino acid transporter. You have one for tryptophan, you have one for lysine, you have one for glycine. You have your transporters to get your amino acids in. These are sodium co-transporters, and they'll take individual amino acids. But if some only get broken down into 2s and 3s, you have a second kind of transporter driven by hydrogen, which will take those guys. This is an important point to remember, because if somebody has a genetic inability to absorb an amino acid, tryptophan is the most common deficiency. You can't absorb tryptophan, and it's an essential amino acid. You got to have it. So you can't just give somebody tryptophan by mouth because they can't absorb it. But you can give it as a dipeptide, and it can be absorbed here. So the di and tripeptides clean up the rest of the stuff that didn't get broken all the way down, so you're able to actually absorb all of your amino acids. So, summarize: pepsin from the stomach, from pepsinogen activated by hydrochloric acid. Pancreatic juice brings in your proenzymes, which become trypsin, chymotrypsin, and carboxypeptidase after being activated by enterokinase. And then your enteric brush border peptidases, which break them down into individual amino acids mostly, but also 2s and 3s, which have their own transporter. So now they've actually made it across the border into the cell, but they're not in the blood yet. So we've got to get all of this actually into the bloodstream. You've got this large cross-sectional area. You're absorbing all of this stuff. It's gotten into the enterocytes now. You got to get it in there. You're also pulling a lot of water in because it's drawn in by all of this osmotic force. When you absorb solute, the water gets pulled by osmosis, and so you're absorbing tons of water at the same time. A lot of carbohydrate, fat, and protein. The absorption of carbohydrates and proteins are both pretty easy. You are forcing them in the luminal side, the side next to the food. Remember, you have those sodium cotransporters and hydrogen cotransporters. You jam it in that side, so all you need are the right size holes in the other side. Facilitated diffusion, and it runs out the other side. So in this case, your driving force are those cotransporters on the luminal membrane pulling it in, and then you have facilitated diffusers on the other side that push it out into the bloodstream. So that's pretty easy. I mean, if we're going to do that sequence like I did for carbs, you can say, hey, you chew up your protein, you swallow it. It stimulates the release of gastrin, histamine, release of hydrochloric acid. The hydrochloric acid unravels the stuff, it denatures it, and your pepsinogen is converted to pepsin by hydrochloric acid, and it starts digesting the protein. Protein enters the duodenum. CCK is stimulated, so you release a lot of pancreatic juice and, liver juices into the lumen of the duodenum. The pancreatic proteases get activated. They digest the large proteins into really small proteins, or peptides. And then your intestinal wall digests them into amino acids that have their own transporter, 2s and 3s that have their own transporter, and they're being pulled in that side or pushed in that side so they are able to just move out the other side by facilitated diffusion. Okay, so that's the whole sequence for proteins. But fats, of course, have to be different. You got to have something more because fats are not water soluble, and so we already, we brought them into the lumen of the intestine. CCK was released, and you get your pancreatic lipases and your bile. The bile emulsifies it, then it's digested, reforms into micelles, bumps into the wall, and moves across the intestinal wall into the cell. And then what's really bizarre is that you reform it into triglycerides. You went to all the trouble to break it down, and now you turn it back into triglycerides, and you do this inside those brush border cells. In the a smooth endoplasmic reticulum, you turn it back into triglycerides, and then the Golgi apparatus, which is your packaging system, packages it into large lipoproteins called chylomicrons. Great. So now you have yet another blob to learn. You got your big blob that gets emulsified into little blobs with bile, digested, reforms into micelles, yet another blob, bangs into the brush border and crosses, gets reformed into triglycerides, and now it has to form into yet another blob, chylomicrons. And chylomicrons are so big they can't be absorbed in your capillaries, into your blood. So they exit the basolateral cell membrane, the opposite side from your food. They exit by exocytosis, because they're so big, they have to use exocytosis to get them out. They can't cross the capillary membrane, so they're sucked into the lymphatic system, which, as we know, can take really big stuff. Here we have a picture of it. Here's a cell. It's releasing chylomicrons by exocytosis. It's now out in the interstitial fluid. It gets pulled into the lymphatic capillaries, enters the lymph system, and works its way up, all the way up to the upper body where it's dumped into the general circulation up there. I love this. This actually shows the whole thing. Once you have already, emulsified and formed the fat droplets, and you digest it and turn it into chylomicrons, and the chylomicrons come here. And so here are your monoglycerides and free fatty acids. They come across, they get repackaged into triglycerides in the smooth endoplasmic reticulum. The Golgi apparetus reforms them into chylomicrons. Exocytosis out into the interstitial fluid. They have to bypass your blood vessel because they don't go in. They're taken in by the lymphatic system, and they move their way into the circulation that way. So it's all on here. Now, once it's dumped into the general circulation, it works its way to the liver, because that's where you need all of your nutrients to go. Remember, the portal system takes your carbohydrates and proteins and your micronutrients like vitamins and minerals and stuff to the liver to be processed before it goes anywhere else. Well, now this fat's got to make it to the liver too, because the liver is going to use these chylomicrons to make your HDL and LDL cholesterols and VLDL cholesterol stuff. So it makes your lipoproteins. On the way there, though, your chylomicrons, as they're floating along in your bloodstream, they are constantly releasing free fatty acids to cells that need them for energy, because we know we can use fat through the Krebs cycle and stuff to make energy inside muscle cells and the like. So by the time that chylomicron reaches the liver, it's called a chylomicron remnant. A lot of the triglycerides are gone. What it has is a lot of cholesterol and stuff in it, the stuff that you need to make your HDL and LDLs out of. So, what do we do with fats? Well, we say pretty much it starts in the intestine. Fat enters the intestine, CCK gets released, it causes bile to come in from the liver, it causes your pancreatic lipase to enter into the sphincter of Oddi along with it, hepatopancreatic duct, your manual calls it. It emulsifies the fat into tiny droplets. The pancreatic lipase digests it, it reforms into micelles, bumps and crosses the border. And by the way, when the micelle releases the fats across the border, the bile stays behind and works some more. The bile works over and over again. It keeps doing this, releasing the fat, doing it again, releasing the fat. The bile stays in your intestine. It doesn't cross there. Well, let me tell you, because I'm not sure I'll remember to say this later, but when the bile is done helping with digestion, it makes it all the way to the ileum, the last part of your intestine. And it gets absorbed in bile transporters there and recycles and goes back to your liver and gets used again. So the ileum, when you get to the ileum, your main things that you got to do there that you can't do anywhere else, you absorb B12, an intrinsic factor, and you absorb bile, B and B. If the ileum isn't functioning, you can't absorb vitamin B12 and you can't absorb bile. And so you wind up pooping out the bile and you have to make a lot more of it. Now your micronutrients are vitamins and minerals. We won't spend a ton of time with them except just a couple of the more kind of different ones. Fat-soluble vitamins simply go in with the fat. When the fat goes, the vitamins go along with it. That's easy. So they go in with the they go in the droplets, they go in the micelles, they go into the cell, they go in the chylomicrons, they go into the lymphatic system, they go into the bloodstream. They just move with the fat. Water-soluble vitamins have a variety of their own individual transporters. That's fine. That's good enough. Except a couple of them that are real specific. Calcium and iron are going to be different. We'll spend more time with iron absorption a little bit later. And we also talked about that in the blood system too. Remember, it came in and it became stored as ferritin, and then it came out and was transported as transferrin, and it wound up in the making hemoglobin inside the bone and stuff. So iron has its kind of own thing that it does. Calcium has specific calcium transporters that have to be activated by vitamin D. So this is why, if you're low on vitamin D, you become calcium deficient, because you can't absorb calcium. Vitamin D is made in your skin from the sun. It's activated by the kidneys. Remember, that's one thing your kidneys do to help you increase calcium. And with the help from parathyroid hormone. Remember, that's your calcium increaser. Parathyroid hormone helps activate vitamin D, so it can help activate your calcium transporter, so you can absorb more calcium. Need vitamin D and calcium. Water is absorbed by osmosis. When you absorb all this other stuff, water is pulled by osmosis. And we've already mentioned vitamin B12. It's a different kind of a guy. It mostly comes from meat or vitamin B12 supplements. Intrinsic factor is produced in the stomach. As you digest the protein and release the B12, it binds to this intrinsic factor either in the stomach or down in the ileum. I mean, in the duodenum, in the very proximal duodenum. You bind your B12 to intrinsic factor. It floats all the way through the small intestine down to the ileum, and the ileum has intrinsic factor B12 transporters. They won't suck in B12 unless it's stuck to intrinsic factor, and it brings it across the brush border. So if you have a deficiency in B12 because you're not eating enough, you can eat more B12. If you have a deficiency in B12 because you can't make intrinsic factor, you have to take B12 shots, because eating any more of it wouldn't really help that much. B12 deficiency leads to what's called pernicious anemia. It's a megaloblastic anemia, which means the red blood cells are too large and they won't fit through the capillaries, and it can be lethal. A couple of malabsorption processes. We've already talked about, lactase or sucrase deficiency, or lactose and sucrose sensitivity. And that means that you can't absorb lactose or you can't absorb sucrose, and therefore you wind up with that kind of gas and cramping and diarrhea. There are a couple of other things, though, that are responses to something that your body doesn't handle well. Celiac disease, or celiac sprue. Sprue just means like stomach upset, okay? Celiac or celiac sprue is gluten sensitivity. If you're sensitive to gluten, when you eat anything that has gluten in it, your walls of your intestines swell up, and they become so dense that they can't absorb anything. And you have malabsorption of everything. And it's very rare. It's quite rare. And if you don't have gluten sensitivity, gluten is not going to harm you. We evolved eating bread. Gluten sensitivity is not a problem for people who absorb things normally, just like sugar is not a problem for people who have normal sugar processing, unless you eat too much of it and you get fat, or you don't brush your teeth and you get, cavities. But your body is designed to handle these. But if you can't, gluten sensitivity. The brush border swells up. The microvilli become packed together or flattened out in such a way that they can't absorb. Malabsorption of nutrients, and a lot of GI upset, diarrhea, and the like. Tropical sprue is Montezuma's revenge. This is when you get a bacterial infection that causes exactly the same thing. You swell up, your intestinal wall swells up, nutrient deficiency, and diarrhea. You can treat this with antibiotics. Crohn's disease, the same symptoms, but it's caused by your own immune system attacking your own intestinal walls. It causes your intestinal walls to inflame, to swell up. You result in malabsorption, osmotic diarrhea, a lot of pain, a lot of cramping, malabsorption. You can't absorb your nutrients properly. So whether it's Crohn's disease, tropical sprue, or gluten sensitivity, the signs and symptoms are pretty similar. It's just caused by different processes. And it's not terribly uncommon, unfortunately, to lose part of the GI tract, to injury, to a blockage where they have to cut it out, to cancer, or something. If you lose some parts of the GI tract, remember the GI tract has, below the normal cells, it has a lot of stem cells that are able to become different kinds of cells. And if you lose like a good part of your jejunum, the other parts of the intestine will start doing some of its work. And you can recover a decent amount, a colostomy, where you can't actually even send your nutrients through the colon because your colon was removed because it was cancerous or something. Other parts of your intestine take up at least some of the slack. Some things, though, that won't work, you can't really absorb B12 if you remove the ileum. Remember, the ileum, B12, and bile, that's a primary job of the ileum, is to absorb that. If you remove the ileum, you're going to have to take B12 shots the rest of your life. Okay, that's the end of that one. I will be posting the other one soon, the second one for this week.